Hey everyone, welcome back to Calculus 3. This will be lecture 13 of the course. And in this section, we're going to discuss limits and continuity. And limits and continuity specifically in the case of functions with several independent variables. So the multivariate case. A lot of this will mirror the discussion we had back in Calculus 1 when we discussed limits and continuity in the context of functions of a single independent variable. But it's going to be slightly different in spots due to the multivariate scenario. Okay, so let's jump into it. Again, this will be section 3.2, limits and continuity. Okay, so we're going to start to begin the discussion. We'll need to discuss what the two-dimensional analog is of an interval. So what is the two-dimensional analog of an interval? Okay, well, it's what we call there's got a couple different names. It's one of the names that is used is a disk. Okay, we also have this idea of a delta neighborhood or just a neighborhood. These are similar concepts. Probably identical concepts in the main, but they take the place, they play the part of the interval that the interval plays in single dimensional calculus. They play that part in two-dimensional calculus. And so let's define a delta neighborhood here quickly. So we can define a delta neighborhood. Okay, a delta neighborhood about a certain point. Right, that just means centered at that point. So we can define a delta neighborhood about x0, y0 to be the disk, okay, centered at x0, y0, with radius delta. Okay, and in this case, delta has to be greater than 0. Okay, so delta is a positive value. Okay, so kind of a more compact way to write this would be to write it in this sort of notation. This is going to be all xy such that x minus x0 squared plus y minus y0 squared, the square root of that, is less than delta. Okay, now what does this mean? Well, this is the distance formula. Okay, obviously delta is greater than 0. So we need everything so the disk, this is the disk. The disk is going to be all points xy such that the distance from xy to x0, y0 is less than delta. Okay, and so this is what we mean by a delta neighborhood about a particular point x0, y0. So let's draw a picture. It's kind of easier probably to visualize if you see it in a picture. Okay, so say we've got some point x0, y0, and this is of course in the xy plane, okay, in a two-dimensional plane. And if we define some distance delta, okay, then the disk is just going to be the circle that kind of surrounds this point x0, y0 that has radius delta. Okay. And so this would be a kind of pictorial representation of this disk. Okay, so the distance for every point in this disk, the distance is less than delta, right? In order for the distance to be equal to delta, the point would have to fall precisely on this boundary. Okay, now it's important to note that in this expression, we use the strictly less than sign. Okay, and in this expression, this the definition involves this strictly less than sign. This indicates that the boundary value is not included. Okay, so let's write that down. The boundary value is not included. Okay. And what this actually implies is that this is an open disk, kind of analogous to an open interval, right? On an open interval, the lower and upper bounds are not included in the interval. Same idea here on an open disk. The boundary values, all the values that would fall exactly on the boundary, be exactly delta away from x naught, y naught. Those values are not included in this open disk. Right? You could easily create a closed disk. Right? It'd be the same basic structure. We would just change the inequality slightly. To be less than or equal to. Right? Otherwise identical formulation. Okay? And so this is kind of the starting point for limits and continuity. We have to be able to discuss these disks. What do we mean by this? Okay. There's a further concept here, and that is the concept of an interior point. And we'll just kind of quickly define this. A point x naught, y naught is in the plane. In the plane region R, I will say. We'll say, so a point x naught, y naught in the plane region R is an interior point. Okay, it's an interior point of R if there exists a delta neighborhood about x naught, y naught, right? That lies entirely in R. Okay. Well, what do we mean here? What are we talking about? Well, let's go back to the picture here. So I've got my x-axis and my y-axis here, right? And somewhere in here I've got a region R, right? Now this doesn't have to be a perfect disk, it can just be whatever. Okay, and so I've got this region R. Now this region is going to naturally have some boundary. Okay, so it's got this boundary. Now if I draw a point right here, for example, then this is clearly an interior point because it is very easy for me to draw a delta neighborhood around the point such that every point in the delta neighborhood is entirely in R. Okay. Now, in fact, I can get arbitrarily close, because these delta neighborhoods can be as small as you like. I can get arbitrarily close to this to the boundary and still have an interior point. All right, so let's put one really close to it. It's kind of right up there, right? Well, I certainly can't define a delta neighborhood as big as this one around this point, but it's still possible for me to define one. Right? It's still possible for me to think of a delta small enough such that every point in the delta in that delta neighborhood about this point here is entirely in R. So this would be another example of an interior point. And now obviously the limits of being able to draw with a ballpoint pen come into play here. But you can imagine that if I were to zoom in on this, very, very close to this, to this piece of the image, I could draw a point even closer to that boundary, and then even closer and to infinity, right? I could do this forever. There are points, however, that would not be interior points. If I were to put a point precisely on the boundary, right, then it is not possible, it is no longer possible for me to define a delta neighborhood such that every point in the neighborhood is within R, right? No matter how small I make the delta neighborhood, because the point lies precisely on the boundary, there is going to be some points, namely you can see up here, that are going to fall outside of the region. Okay, so that's the idea with an interior point. Okay, and so if every point in R is an interior point, then we say R is an open region. An open region. Okay, and that's going to go kind of take us back to this image here, right? So in this image, it's not possible for me to draw, put a point on precisely on the boundary, right? Because the boundary is not included, right? So that's the idea here. And as I say, you have to use your imagination. You have to think about what would happen if I were to zoom in on this line closer and closer and closer, and you have to accept the idea that I could keep getting indefinitely close to that border without precisely being on the border. Okay. All right, so that is kind of our starting point. So the key idea here is the delta neighborhood and how that's thought of as a disk, right, centered at whatever the point of interest is. Okay, and so using this setup, we can define the limit of a two-dimensional function. And really this would extend to higher functions pretty naturally, but we'll just kind of write it in terms of a function of two variables. Okay, so definition. Let f be a function of two variables, and we'll say defined on an open disk centered at x0, y0. Okay, and we say it's defined on an open disk centered at x0, y0, but it could possibly be undefined at x0, y0, right? We'll let L be a real number. Then, right, so here's the definition. The limit as xy approaches x0, y0 of the function f of xy. So that limit is equal to L if for each epsilon greater than 0 given, there exists a delta greater than 0 such that, right, so such that f of xy minus L is less than epsilon whenever 0 is less than the distance function here, x minus x0 squared plus y minus y0 squared, square root of that, and that needs to be less than delta. Right, so whenever my xy's are within delta of the limit point x0, y0, then my function needs to be within epsilon of the limit value. Okay, so very similar. I mean, literally the same idea as what you'd get with the one variable definition, right? Except here we're talking about an open disk. There we were talking about an interval, right? And you can imagine that as we extend this definition into higher dimensions, right, the only thing that really changes is the notation that is needed to define the intervals, right? The construct that is required to define the analog of the interval. Okay. Now, one thing to note about about this about limits in general when you have two variables is that, in the case of one variable, right? In the case of one variable, right? In the case of like f of x, we needed we needed the limit as x approached a from the right to be equal to the limit as x approaches a from the left, right? And so in this case, you had some function, right, and then some point a, and we needed the approaches from both directions to produce the same value in order for the limit to exist. In the case of just moving into this two variable space, right, the situation becomes somewhat more complex. So now when we think about the xy plane, that's sort of the domain, right? So that takes the place of the line here, right? And so if we have some limit point x naught y naught, we need to be able to approach it from any direction and have the limits be the same, right? So as we approach x naught y naught in the xy plane, there's some third axis extending out of this, which is the value of the function, right? And we need that value to be identical no matter which direction we approach x naught y naught from. Okay, so to kind of put it succinctly, if the value of the limit as xy approaches x naught y naught of f of xy is not the same for all approaches, okay, then the limit does not exist. Okay, so that's that's a subtle difference, but I think it's, hopefully that's intuitive. It's the same idea, right? So, instead of a line with an interval, right, now we've got a space, a flat space, a 2D space with a disk, right? So we need to be able to approach x naught y naught from any direction and have the value of the function be the same as, have the limit of the value of the function be the same from on any path in the disk. So that's obviously a stronger kind of, it's a more demanding requirement. Well, it's just a more complex way to think about things. Okay, let's do an example. Let's actually crank out one of these proofs here and see how these typically work. So we'll sort of do a simple one just to kind of get the feel for this. Let's show that the limit as xy approaches AB of f of, let me rewrite this, sorry. So let's let f of xy equal x, okay? And let's show that the limit as xy approaches AB of x is equal to a, right? So kind of a simple example here. Okay, so let's show this one. Okay, and so just kind of, again, we're just going through this example because we want to think about how to set up these proofs, what kind of chain of reasoning needs to be established. Okay, so let's start by letting f of xy, equal x. We kind of have that. And in the notation for the definition of the limit, we had an L, and so that L in this case needs to be equal to A. Okay. Now, what do we need to show here? What are we trying to show? So we need to show we need to show that for each epsilon, right, any epsilon you give me, there exists some delta neighborhood. Right? For each epsilon greater than 0, there exists a delta neighborhood such that whenever, whenever 0 is less than x minus a squared plus y minus b squared, square root of that is less than delta. So whenever our xy is within delta of ab, then we have the following: f of xy minus L equals x minus a is less than epsilon. Okay, that's what we need to show. All right, so somebody gives you an epsilon, and from that epsilon you have to find a delta such that whenever you're within delta, whenever your xy's are within delta of AB, then the value, the function, is within epsilon of L. Okay, so that's the idea. Almost identical in structure to the epsilon delta proofs we saw in Calculus 1. Okay, and so really the key here, really the key to a lot of these is identifying what value of delta will work, right? And there may be several, right? There may be multiple values of delta that you may be able to identify, but just identifying some delta that makes the inequalities hold. Okay, and so for this example, you'd really kind of want to start with this piece of the expression here and sort of figure out what that looks like in terms of this distance formula. Right, so let's start with that. Right, so we start with f of xy minus L. Now f of xy is just x, right? And L is just a. Right, so that's why this is sort of an easier example. Right, so you get this pretty quickly. So that's just the absolute value of x minus a. And so we can easily convert this into this distance formula by just taking, just squaring this difference and taking the square root. Okay, so we've got this easy chain of equality here. And then this isn't quite this, so we could throw the y component on there as well. But when we do that, we have to say less than or equal to. Right? Because certainly if we add some quantity under here, it's going to potentially grow this, right? If the quantity is non-zero. Right? So that's less than or equal to x minus a squared, which is just that piece, but then we'll put this other piece on as well. Okay. And then what we need to do is get this thing here to be less than within delta, right? And so we know that this is going to be less than delta. Right? And so this expression here tells us that we can set our delta directly equal to epsilon. Okay. And now let's talk it through. So this is kind of the reverse. In order to actually solve these, you have to kind of think about it in reverse, figure out what this delta needs to be set to, and it's got to be something in terms of epsilon. Right, and then you can reverse the argument and start from the standpoint of an arbitrary epsilon, and arbitrary epsilon can be used to produce whatever delta is needed. Right, so now we can just flip the expression and restate this. Okay, so to restate, right, I guess this isn't really a restatement. This is more like a statement. The first thing, this bit up here is just kind of problem solving. Right, now let's actually restate the expression. Okay, so let epsilon greater than 0 be given. All right, so someone gives you some arbitrary epsilon, right? And so, somebody gives you an arbitrary epsilon, and then you say, all right, so let epsilon greater than 0 be given. Choose a delta that's equal to epsilon. In this case, this won't always be the case. In this case, it's going to work. So then whenever, x and the value of xy, the point xy is within delta. So another way to say that is that whenever 0 is less than the distance between x minus a squared plus y minus b squared, right? That's the distance between xy and ab. Whenever that's less than delta, we have what? What would we have? Well, kind of just restating what we worked out up here, but we would say, okay, starting with this thing, that is just, in this case, x minus a, and that's equal to x minus a quantity squared, the square root, which is less than or equal to x minus a quantity squared plus y minus b quantity squared, right? Which is, now this piece here is less than delta by assumption, right? So we have assumed whenever xy is within delta of ab, then it's, obviously it's going to be less than delta, and we've chosen our delta to be exactly equal to epsilon, right? And so what have we shown here? We've shown that if xy is less than delta away from ab, then f of xy minus L is less than epsilon. So f of xy is within epsilon of the limit L. Okay. So this was kind of a simple example. Right? These can be obviously as complex as you like, but the idea will be the same pretty much throughout. Okay. Let's evaluate a limit. Okay, now a lot of the pretty much all of the principles of limits that we had in Calculus 1 can be applied to these multivariate functions as well, right? So, for example, the limit of a product is equal to the product of the limits. The limit of a quotient is equal to the quotient of the limits. The limit of a sum is equal to the sum of the limits, that kind of thing. So keeping that in mind, let's take a look at this example. Let's evaluate the limit as xy goes to 1, 2 of this function, 5x squared y over x squared plus y squared. Okay, so let's evaluate this function. Well, this function, you can this is a rational function, right? And so you can basically, we know that for each of, in the case of the numerator and the denominator, they're both polynomials, so the limit is, there's continuity there, so we can just plug those values in, right? So the limit as xy approaches 1, 2 of 5x squared y, well, that's just 5 times 1 squared times 2, which is 10, right? And we know that the limit as xy approaches 1, 2 of x squared plus y squared, that's equal to 1 squared plus 2 squared, right? And so that's equal to 5. And so again, kind of like what we sort of started with this, but because the limit of a quotient is the quotient of the limits, we have, what do we have? Well, the limit as xy approaches 1, 2 of 5x squared y over x squared plus y squared, well, that's equal to the quotient of the limits, right? So we take the limit on the top of the top part and divide that by the limit of the bottom part, right? And so we did that up above here, and so this is just 10 over 5, and so it's 2. So a lot of the same kinds of properties can be used in the case of limits of multivariate functions. Okay, so let's do another example where we try to Let's do another kind of proofy example. The first one was very simple. Let's take a look at this one. We're going to use the same function as the previous example, but here we're going to verify that the limit as xy approaches 0, 0 of 5x squared y over x squared plus y squared. We're going to verify that that is equal to 0. Okay, now this one is actually kind of tricky to evaluate because you'll notice that the limit of the numerator and the denominator is both 0, and that's an indeterminate form. So actually to evaluate this one, you'd have to take there'd be quite a little bit of work that you would have to do. Right, but we're going to just take as given that this limit is indeed 0. Okay, and I'm just going to actually work this proof the correct direction. I'm not going to fill in all the back detail, but I'll indicate what the back detail is, and then you can confirm that on your own. Right, so we would start this proof by saying let epsilon greater than 0 be given, which is another way of saying let epsilon be an arbitrary value, right? It could be arbitrarily small. And let's choose delta equal to whatever epsilon is divided by 5. Let's divide it down by 5. So epsilon can be 0.000001, then delta is just 0.000001 divided by 5. Okay, which is clearly a real number. We can do that, no problem. Okay, so epsilon's given. We choose delta based on this epsilon to be equal to 1/5 of it. Okay, then let's assume that our xy is within delta of 0, 0. So this is kind of the English way of saying it, but let's assume that xy is within delta of 0, 0. And what does that mean? Well, which means 0 is less than, so x minus 0 squared plus y minus 0 squared less than delta. Okay, so we're assuming xy was whatever delta happens to be, which is based on epsilon. We're going to assume xy is within that distance of 0, 0. So we're probably very close to 0, 0. Right, and so notice that because the limit point is 0, 0, this even simplifies further down to 0 less than x squared plus y squared less than delta. Okay, so it's even simpler. Okay, so we know that x and y, so we know basically that the square root of x squared plus y squared is less than delta. Then, what does that imply? Well, here's where we have to go, and we'd have to go off to the side and do some work on the expression, but here's what you could get to. Right, we want to show that this is with less than epsilon. Well, this is just the starting expression. Let's plug in the actual quantities now, and the function f of x, or 5x squared y over x squared plus y squared, and then minus the limit value, which is 0. Right, that's what we're told up here. Okay, and so this, of course, is just 5x squared y over x squared plus y squared. Okay. Now, we can pull the 5 and the y out of here. Okay, and so let's do that. When I pull the y out, I have to put it in absolute value, but that allows me to make the rest of it not an absolute value. I can pull the rest of it out of the absolute value here, right? So, and why can I do that? Well, because these terms are all squared. These pieces of the expression are all squared, so they're clearly positive, right? And the sum of two positives is clearly positive. Okay, so I can get down to this. Now, here's one move that is a little bit tricky. This quantity here is less than or equal to 5 times y. Now, why is that? Why is this? Well, this is because this piece of it here, this x squared over x squared plus y squared, that's definitely going to be less than or equal to 1, isn't it? right? So this, if this is 1, then this whole side is just 5 times the absolute value of y. If this is something less than 1, then this whole side here is less than 5 times the absolute value of y. So if this is less than 1, then clearly this times that is going to be less than that. All right, so it's kind of a subtle thing, but it allows us to simplify this expression. Okay, and now what can we do going from here to the next piece? Well, the next thing that's also kind of tricky is we can see that this is less than or equal to 5 times the square root of x squared plus y squared. And why is that? Where does that come from? Well, specifically, this is saying that the absolute value of y must be less than or equal to the square root of x squared plus y squared. Now, if x is 0, then these are equal, right? But if x is any quantity, you know, positive or negative, then when I square it, it's going to add to the size of this side, right? So clearly this piece here is less than this piece here. This piece here is less than this piece here, or potentially equal if x is 0. Okay, and so then what? Well, so then I'm gonna kind of move down here, give myself a little more space. Okay, and so this here, this is square root of x squared plus y squared. If we just look up a little bit, we can see that that's right here. So this here is less than delta, 5 times delta, sorry. Right, so that's strictly less than 5 times delta, right? Because x squared plus y, square root of x squared plus y squared is strictly less than delta. So this must be strictly less than 5 delta. And that's where we can plug in our epsilon, because we know that delta is equal to epsilon over 5. So this would be equal to 5 times epsilon over 5. And of course, this is just equal to epsilon. Okay, so we've shown that this piece here is less than, right, strictly less than, we got less than here, epsilon. So we've shown that f of x y minus L is less than epsilon whenever 0 is less than x squared plus y squared, which is less than delta. Okay, so we've shown that piece. All right, so that's the proof. That's the proof, end to end. And so there's a little bit more work involved in this one, right? Well, I mean, most of these things are relatively obvious, but you know, if you're kind of new to doing epsilon delta proofs, these could be somewhat tricky. It's it would have, you know, these arguments are a little bit more self-directed than what most Calculus 3 students are used to, right? So you have to sort of direct that direct the argument in the direction you want it to go, which is something that you're not really, most students at this level aren't really accustomed to doing. So these could be a little tricky. Again, Calculus 3 is not usually the place to emphasize proofs like this. It's not really until you get into analysis where this sort of thing becomes kind of the point of it all. Okay. All right. Very good. And so now we have this idea of a limit, and so we can extend our section into the continuity discussion. So let's talk about and define continuity for a multivariate function. So a function f of 2 variables is continuous at a point x naught y naught, okay, in an open region R if, right, if f of x naught y naught is equal to the limit of f of xy as xy approaches x naught y naught. I don't know why I wrote that out. Another way to say it would be to say if the limit of xy as it approaches x naught y naught, the limit as xy approaches x naught y naught of f of xy equals f of x naught y naught. There we go. Right, so that's basically the same definition of continuity that we had in Calculus 1. Okay. And so this is continuity at a point. What do we need? What needs to be true in order for the function to be continuous on all of R, on the open region R? Well, it just has to be continuous at every point in the open region R. Okay, so I won't write that, but it's the same idea as what we had on from Calc 1 when we said that a function is continuous on an interval if it's continuous at every point in the interval. Okay. All right. Very good. So let's jump to some theorems here. Okay. Let's say if k is a real number, k is in R, and f and g are continuous at x naught y naught, then the following functions are also continuous. Okay, so the following functions are also continuous, and so these are just going to be the product k times the function f. Okay, so this is the scalar product, and then the sum of the functions f and g, or the difference. The product of the functions would also be continuous. Right, if I multiply the two functions together, then the resulting function will be continuous. And if I divide, we have continuity as well, provided, of course, that g of x naught y naught is non-zero. If the denominator is 0, then you don't have continuity. Okay. All right. Very good. Very good. Now, so this is basically all of the combinations of f and g that you can have, except for the composite function. Right, we talked about the composite function in the previous section and how some special consideration has to be given to composite functions when the functions are multivariate. Right, and so in particular, we said that you can only compose a multivariate function with a single variable function. Right, we can't plug two variables into the outer function, right? And that's all that is kind of required for this theorem as well. So if h is continuous at x naught y naught, and g is continuous at whatever value you get for h x naught y naught, right? So it's a single value. So if g is continuous at this particular value, then the composite function g composed of h is continuous at x naught y naught as well. Okay, another way to say that is that the limit as xy approaches x naught y naught of g composed of h of x y. So continuity means that this would be g of h of x naught y naught. Right, and so here you see the issue with the composition of multivariate functions. So g is a function of a single variable, right? When you plug x naught and y naught into h, you get a single value out, and that single value is the argument for g, right? And so the continuity is defined naturally in the case of compositions like that. Okay. All right. Very good. So this gets us almost to the end of the section. So, I mean, again, a lot of the deeper discussion of continuity and limits here is, you know, kind of abbreviating some of it, partly because that was covered in a lot of detail, you know, in Calculus 1 when we were first exposed to the idea of continuity and of limits, but also partly because there's only so much we can discuss in Calculus 3 that you know, without intruding into the realm of real analysis, right? And specifically with limits and continuity, that's a big topic in real analysis. Here we're a little more concerned with getting, you know, we're a little more interested in the results and how to use the results, and then in analysis we're really the point of analysis is to dig into all of these theorems in tremendous, excruciating detail. So here we're kind of flying over it. But okay, let's talk through one more example, quick, kind of a shorter example. But given a function, where is it continuous? Where is the function f of xy equal to x minus 2y over x squared plus y squared? Where is this continuous? Well, I mean, this kind of question, really, to understand this kind of question, you really have to just kind of think about what sort of function are you dealing with. And this is a rational function, isn't it? It's a ratio of two polynomials, right? So this is a rational function. Rational functions are, you know, the ratio of two polynomials. Polynomials are continuous for all values in their domain, right? So this is a rational function. This is a rational function. That means it is a ratio of two polynomials, right? Polynomials are continuous for all values in their domain. Now, that doesn't mean a rational function is continuous for all values in the polynomial's domain, right? For all values of R, right? In particular, in this case, there's one point where this rational function will not be continuous, and that is the point that would fall outside of its domain, specifically the point xy equals 0, 0. Right? So this function is not continuous at xy equals 0, 0, specifically because that value, this function is undefined at that value, right? So it clearly can't be continuous. So f is continuous on what? Well, it would be all x, y in R2, right, such that x, y is not equal to 0, 0. So it'd be continuous everywhere, except at the origin. Okay, and so this will have some kind of a hole at the origin, right? So it's not defined there. Okay. All right. Very good. So this has been, again, kind of an introduction to limits and continuity in the multivariate case. Now, all of these things can be extended into higher dimensions yet, right? So functions of 3 independent variables, 4 independent variables. The only thing that changes is the distance function, right? So the distance function is going to change. The distance function that's used to define the delta neighborhoods. Otherwise, most of the stuff kind of carries over naturally into higher dimensions, right? It just becomes very difficult to visualize it or to, you know, explain it. So we start with just functions of 2 variables because that's we're really dealing with the XYZ coordinate system for those examples. But everything kind of keeps going into higher dimensions. We'll leave it there for this one. Next time we will move into derivatives. We'll start talking about derivatives, and specifically we'll start talking through what are called partial derivatives. So we have functions of multiple independent variables, and so now let's talk about how to differentiate those things. Okay, and so partial derivatives are actually pretty interesting and pretty fun to deal with. We look forward to that. All right. Well, take care, and we'll talk to you all. We'll talk to you all next time. Take care.